Hello and welcome to Astronomy 121 tutorial on calculus and its physics applications. Here's a brief outline of what we'll be talking about today. First, we'll look at differentiation as a rate of change and recall the definition of the derivative. Then we'll apply that to a problem of uniform acceleration. We'll then go on and talk about some rules of differentiation, such as the product rule and the chain rule. And then we'll spend the rest of the tutorial essentially applying them to physical examples. So let's talk about derivative as a rate of change. Imagine you have some function f of x that looks like this black curve here. And you want to know what the average rate of change of this function is between this red point and this black point here. Well, it's given by the slope of the secant line, which is rise over run. And in this case, it would be f of x2 minus f of x1 divided by x2 minus x1. Now, if you imagine I now slide this point closer to the blue point, again, I have a second secant line for which I could, again, compute the slope. And if you imagine that I keep sliding this point closer and closer and closer and closer to the black point, eventually they would get infinitesimally close to one another. This is precisely the notion of the instantaneous rate of change. That is, the tangent line. In this case, we'll let the run go to 0. The derivative is exactly the slope of this tangent line. So f prime of x, or df by dx, whichever one you prefer, is given by this limit here. That's precisely the slope of this tangent line. So the derivative gives you the instantaneous rate of change of the function. For example, the derivative of position is the velocity. Here are the rules of differentiation. These you should know, and if you need to, you have to memorize them. Especially the first two are very important. The first one is that the derivative of a constant is 0. Intuitively, you should remember that if you draw a constant function, that's a horizontal function. So the slope of this line is, of course, just 0, because there's no rise. And then, very important is the derivative of a power. So if we have d by dx of x to the n, that becomes n times x to the n minus 1. So the degree of the power gets reduced by 1, and you get a factor of n out front. The rest of these you should also remember, so that the derivative of the exponential is the exponential function itself, etc., etc. All of them might come up during the course. Let's see if we can apply this. Suppose that somebody throws up a ball in the air with an initial speed of 20 meters per second. And I tell you that the equation that describes the position of the ball is given by r of t is minus 4.9 t squared plus 20t. Let's compute the velocity and acceleration of the ball as a function of time. The velocity is, of course, the derivative of the position, so v is dr by dt. So we must take the derivative with respect to time of this expression here. So we use our power law, and we end up with minus 9.8 t for the first term. So 2 came down, this 2 became a 1, and you get a minus 9.8 in front. And then there was a 1 here, which came down, so you still have a 20, and t to the 0 is, of course, just 1. So the final answer is minus 9.8 t plus 20. The acceleration is the derivative of the velocity. So a is dv by dt, so we must take d by dt of this expression. And again, if we use our rules, we end up with minus 9.8 meters per second squared. So in this problem, we have assumed that acceleration due to gravity is a constant, which is, of course, only an approximation, as you can remember from the second problem set. But it is very useful when you're close to the surface of the Earth. Now, suppose we actually wanted to know how high this ball would go. There's two ways to solve this problem. The first one is to use the fact that we know what the position and the velocity of the ball are as a function of time. If you recall from the tutorial, at the maximum height, the velocity of the ball must be 0, simply because it changes from going up to falling back down. So we set the velocity equal to 0, and we rearrange this equation and solve for t, and we get that t max is 2.04 seconds. Now, this is still not the final answer because we wanted the maximum height, so we must plug this t max back into our equation for r, and when we do so, we end up with a final answer of 20.4 meters. The second way to solve this problem is to use energy conservation. The advantage of this way is that you don't actually need to know the position or the velocity as functions of time. Let's see how we go about this. When the ball is on the surface of the Earth, we can think of it as only having kinetic energy. So the initial energy that the ball has is 1/2 mv0 squared, where v0 is of course just 20 meters per second. Now at the top, at the maximum height, the energy must be purely potential at that instant. V is equal to 0. It switches from going up to going down. So the energy is purely potential, and we can write it as mg times r max, where g is the acceleration due to gravity, minus 9.8 meters per second squared, and r max is the maximum height. We can then set this expression equal to this expression and rearrange it to solve for r max, and we end up with this with 1/2 v0 squared over g, and if you plug in all the numbers, you'll end up with 20.4 meters, which is exactly the same answer as we had before. Alright, let's move on to more sophisticated rules of differentiation, and these two are the product rule and the chain rule, both of which are extremely important. Suppose you have a function h, which is a product of two functions, f and g, and you want to differentiate h with respect to x. The way you remember this rule is by realizing that the derivative of h with respect to x is the derivative of the first one times the second one plus the first one times the derivative of the second one, where first one and second one refer respectively to f and g. The chain rule applies when you have a composition of two functions. So if h is f composed with g, then the derivative of h with respect to x is the derivative of f with respect to g times the derivative of g with respect to x. So formally speaking, you can actually just cross out these dg's so they cancel out. Of course, that's just a formal trick. You can't actually do that, but it helps you remember what chain rule is. Let's see if we can actually apply this to a real problem. Now, the radioactive decay of a substance is probably familiar to a lot of you. You've probably all heard about carbon dating and so on. And the equation that actually describes radioactive decay is given here. I should mention that it's actually radioactive decay which powers the afterglow of a supernova. Now, in this equation, A is the amount of matter you have at a certain time t, and A0 is the amount of matter you started with. But what is the meaning of this parameter lambda, and what units must it have? To answer this question, consider the amount of time it takes for the substance to decay to 1 over e of its starting amount. That is, A is A0 over e. And we set that equal to A0 e to the minus lambda t. We can cancel the A0s, because they're the same on both sides, and then we remember that 1 over e is nothing more than e to the minus 1. Setting these equal, we must have that the exponents are equal, so 1 is equal to lambda t, or the t decay is 1 over lambda. So the parameter lambda is nothing more than 1 over the time it takes for the amount of matter to decrease by a factor of e. Since lambda, we can rearrange this, is 1 over t decay, lambda must have units of 1 over time, because t, of course, have units of time. But that means that the product, lambda t, is unitless, right? It does not have any physical units. And this is exactly what must happen. One can never have any quantity with units inside an exponential or a logarithm. This is a useful check to make sure that you have actually not done anything wrong. Let's try to apply our rules of differentiation to this problem of exponential decay. Suppose that we want to know what the rate of decay is. In this case, that's simply the derivative of a with respect to time. And we also want to examine the strange ratio of a over dA by dt, absolute value. What does it mean? Well, the rate of decay is computed by using the chain rule. So we take our expression for where a and differentiate with respect to time. If you remember, the derivative of the exponential is nothing more than the exponential itself, so that gives you this term here, but we must also differentiate the expression that's inside the exponential, so that's chain rule, and the derivative, the expression inside the exponential is minus lambda t. The derivative of minus lambda t is just minus lambda. So the final answer that we get is dA by dt is equal to minus lambda a0 e to the minus lambda t. Now, if we take our expression for a and we divide by dA by dt and take the absolute value, we end up with nothing more than just 1 over lambda, which we said was t dk. So, this is a simple example of what we call the characteristic timescale. That's simply the timescale on which the system under consideration changes appreciably. In our case, it's the timescale over which the amount of matter decays by a factor of e. And in general, the concept of characteristic timescale comes up again and again in astronomy. Suppose now you discover some magical element for which lambda is actually time dependent. So lambda is equal to the square root of c times t. And we again want to know what the rate of decay is. Well, in this case, we'll have to use the chain rule and the product rule, and we'll have to use the chain rule twice. So, we want dA by dt. So once more, we take our expression for a, and we differentiate it. We get this e to the minus lambda t times t term, as usual, because we're differentiating the exponential. And then we must take the derivative of what was inside the exponential, and that's d by dt of minus lambda t times t. And I put that's why we get this term here, and I put the minus sign out front. Now, the derivative, d by dt of lambda t times t, these are two different functions, so we must use product rule. So we have the derivative of lambda with respect to time times t, plus lambda times the derivative of t with respect to t. The derivative of t with respect to t is nothing more than 1. So we expect that we can just put lambda for this term here, and that's why we have square root of ct. The derivative of the first term is d by dt of the square root of ct, and I'll leave it as an exercise for you to show that in fact the derivative is 1/2 square root of c over t. If you multiply that by t and you combine these two together, you'll end up with the final answer of dA by dt is minus 3/2 times the square root of ct times a. So that is the rate of change. Now, let's think of another very physical exercise, physical application. Suppose you have a mass in a very stiff spring, and you compress it, say, by some amount x from its equilibrium position. What do you think would happen to the mass? Well, you probably think it will oscillate back and forth, and that's exactly what happens. So here's an animation of this happening. So we have a mass attached by a spring to the wall here, and you see that the position changes, the position indicated by this blue arrow. It keeps oscillating back and forth, back and forth. The red arrow here represents what's called the restoring force, and that's the force due to the stiffness of the spring on the mass. And the equation that represents this restoring force is F is equal to minus kx, where k is some constant, and x is the distance from this red line to the current position of the mass. An interesting thing to realize is that the mass keeps returning to its previous position. So the motion is in fact periodic with some period t. Let's see what we can, whether we can describe this motion mathematically. So here's a question very similar to what we have seen in tutorial. What is the differential equation describing the motion? Well, we know that the force acting on the mass is just the force due to the spring, which, as I have already mentioned, has the form F is equal to minus kx. Notice the minus sign, it's very important. We also know that Newton's law states that the force on an object is the mass of that object times its acceleration. So if we set these two equal to each other, we get ma is equal to minus kx. If you remember, the velocity is the first derivative of the position, so it's dx by dt, and the acceleration is the derivative of the velocity. So that acceleration is the second derivative of position with respect to time. So if I replace a here by d squared x by dt squared, I take this to the other side, so it gets the opposite sign, and I divide by m, I finally end up with this very famous equation, d squared x by dt squared plus k over m times x is equal to 0. That is the equation of the simple harmonic oscillator. What can we say about it? Well, I will not ask you to actually find the solution. Instead, I want you to actually show that this is indeed a solution to this equation, and tell me under which conditions it is a solution, and what is the meaning of this parameter omega in this expression. So if you look at this expression, it's a cosine function with a few parameters, a, omega, and phi. And it sort of makes sense. Remember that the motion was periodic, so it makes sense that the solution should be some periodic function, such as the cosine. But let's verify that this is indeed a solution. The way you do that is you take this expression for x, and you plug it back into this equation, and see whether the left-hand side becomes equal to 0, so that 0 is equal to 0. Well, we need to take the second derivative with x with respect to time, so first we need to compute the first derivative with respect to time. So we take d by dt of a cosine omega t plus phi, where omega and phi are both constants. So we end up with just a minus omega out front. There should be a phi. The second derivative is simply, again, we differentiate this expression now with respect to time, and we end up with minus omega squared out front, and a cosine omega t plus phi. In both of these cases, I have used those rules. The derivative of the cosine is minus sine, that's why there's a minus sign, and the derivative of sine is cosine. So we needed to use chain rule. So let's continue on. If we take those expressions and we plug them back into our equations of motion, so this was that term, the second derivative, and this is our expression for x, so d squared x by dt squared plus k over mx. Let's see, well, we have a cosine omega t plus phi in both of these expressions. Factor them out, and we end up with an expression like this. Well, if we want this to equal to 0, that would be true only if minus omega squared plus k over m is equal to 0. Of course, it would also be equal to 0 if a was 0, but in that case, our solution would just be the trivial solution of nothing is moving anywhere. From this expression here, we can rearrange and solve for omega, which is the square root of k over m. Omega is actually the angular frequency of this periodic motion. You can think of it as an angular speed. The period of our oscillation is given by 2 pi over omega. The way to think about it is that you can think of any oscillation as essentially going around a circle. A circle has 2 pi radians, and omega represents the angular speed of going around the circle. So the time to complete one revolution is however many degrees are in a circle divided by the angular speed, many radians, so you get 2 pi over omega. Incidentally, these a and phi parameters are called the amplitude and the phase of the motion, and they essentially describe the freedom of choosing the initial displacement and the initial velocity of the mass. Remember, you could have made those whatever you wanted. Finally, let's talk about conservation of energy. Now, when the mass is moving, we all know that it has kinetic energy, given as usual by k is equal to 1/2 mv squared. The question is, where is this energy coming from? We remember that the law of conservation of energy states that energy must be conserved, so energy cannot be created or destroyed, it can only change forms, so this must come from somewhere. And unsurprisingly, it comes from the energy stored in the spring. So the spring has some elastic potential energy, which has the form U is equal to 1/2 kx squared, where x is again the displacement from the equilibrium position. That is the position in which the spring is not stretched or compressed. The total energy, evidently, then, is the sum of these two terms. So it's 1/2 mv squared plus 1/2 kx squared. Now, we can actually use this expression and the conservation of energy to answer the question, at which position in its motion is the mass moving the fastest? Now, since the potential energy depends on the distance from the relaxed state, or equilibrium state, when the mass is at the equilibrium state, so when x is equal to 0, this term is, of course, 0, so there's no potential energy. Thus, all the energy that the mass had before must now be in kinetic energy. So it follows that the mass must be traveling the fastest when x is equal to 0, so when it's passing through its equilibrium point.